alcohols, I believe, towards the end there. Remember, alcohols sort of functional group. Let me get this thing to right here. There we go. Try that again. All right, so we have our alcohols. Maybe it's gonna right. There we go. Alcohols. Functional group being that OH group is our functional group for an alcohol. Remember that we can classify alcohols just like we classify pretty much carbons as primary, secondary, or tertiary alcohols. And really, it has to do with the carbon that has the OH group attached to it and how many carbons are basically attached to it. So this would be a primary. Obviously, I didn't draw on the hydrogens. If we had an OH group and this carbon attached to it, then had perhaps two other carbons attached, that would be a secondary, and then obviously a tertiary here would have three carbons attached to it. We talked about how you make an alcohol. You make an alcohol from a hydration reaction of an alkene. So basically what that means is we have a double bond, we add water, which is why it's called hydration. This is one of those unsymmetrical additions. Basically double bond becomes a single bond. OH goes to one, H goes to the other, and that right there makes our alcohol through this hydration reaction. Remember, if these unsymmetrical additions, if there is an option as to the hydrogen would go to the carbon that started with the most hydrogen to begin with. By the way, to go backwards, it's a dehydration reaction, which basically means you take water out. So that's the H and the OH come out, and then you put back the double bond. We also talked about that oxidation reduction reactions with alcohols. Wrong button there. A primary alcohol. And again, we'll just kind of draw a quick one here. Got a primary alcohol, looks something like this, perhaps. Goes through an oxidation. Always what happens is we're going to take off a hydrogen from the OH, hydrogen from the carbon that's attached there, and that's going to give us our H2 that comes off. And remember, as we talked about, nothing else changes other than we're going to now make a double bond where we took out the hydrogens. And we end up with this guy right here, which is the functional group of a aldehyde. And with primary alcohol. Going backwards is the reduction reaction, where basically we would add a hydrogen back to this spot, add a hydrogen back to this spot, double bond would become a single bond, and we would get back our alcohol here. And I'm sorry, I drew the wrong spot there. Let me correct that there. Actually, we would add the second hydrogen to this carbon here. There we go. That's better. And obviously that double bond there between the carbon and oxygen would go away. We also talked about that, as we'll talk about in another chapter as well. This can further be oxidized. And in this case, we're going to actually add oxygen, which is a definition of oxidation. And this can go one more step into a carboxylic acid, which is this guy here, carboxylic acid. So one oxidation of a primary alcohol yields you an aldehyde. If you actually oxidize the aldehyde, you end up with your carboxylic acid. We also talked about that a secondary alcohol can also go through oxidation. So we'll just do this maybe. Excuse me. We'll do this and we'll do that there. Is that my way here? Thank you. So we'll do our OH here by get it out. There we go. So we got our secondary alcohol, again, going through oxidation, going to take the H from the O, H from the carbon. And again, we're going to double bond it up there. Remember, nothing else changes. Everything stays the same, except that obviously we put our double bond in there. And what we end up with is a ketone plus H2. Functional group of a ketone, I'll just highlight it, is basically the 3 carbon run with the OH group basically attached. So that is a ketone. And obviously the reduction part would be the opposite. We could put the H2 back on, and we could actually take the ketone back to a secondary alcohol. Again, a hydrogen would go here, hydrogen would go here, going in the opposite way. Double bond becomes a single bond, and we would get our alcohol back. Lastly, we talked about a tertiary alcohol, which basically looks something like this. If you try to go through an oxidation, will not occur. It does have the hydrogen here, but it is missing the hydrogen there. So it cannot go through oxidation. So that's sort of what I believe we talked about last time. Any questions on any of that stuff there before we continue on? Okay, then let us continue on to sort of another functional group. And that functional group is thiols, I believe. That's what we got coming up here. So thiols are, excuse me, thiols are groups or organic groups that contain sulfur and basically have a functional group that looks almost like the alcohol. It is the SH group basically on there. It has similar sort of characteristics than an alcohol, because if you look on an alcohol or on the periodic table, that is where oxygen is located, and right underneath it is sulfur. So they do share very similar sort of properties. As you could probably tell from the skunk here, not the greatest smelling things that contain sulfur. Also, sulfur is put into, like, gas lines, so you could kind of smell it if there actually is a gas leak, which I guess is a good thing. But they're kind of similar in terms of functional group to an alcohol, but a little bit different again, because we're dealing here with sulfur. It doesn't have the ability to hydrogen bond, because we have a hydrogen bond to sulfur and not nitrogen, oxygen, and fluorine. So it cannot hydrogen bond like sort of an alcohol. How do we name thiols? Well, simply, you don't have to worry about naming thiols, but basically we kind of just put thiol there at the end is one way that you can name it. Again, here, this is basically a methane group, 1 carbon, and we just put thiol at the end of it. So methane thiol, ethane thiol with our 2 carbon group. And obviously we have a 4 carbon group here, which is based off of butane thiol. And the location of where this guy is at is carbon number 2. In this case, there's more than 1 spot. So just like an alcohol, kind of there's more than 1 place where you could put it. We usually run into that about 3 or more carbons. We do have to give the number where the SH group is. So you don't actually have to worry about the naming aspect of thiols, but you do need to know the functional group. You also need to know an important sort of reaction the thiols undergo, and that is also an oxidation reaction. So if you had 2 thiols, just say we take this guy, and maybe we react it with another thiol here. And we'll give it a couple extra carbons here. It actually will go through an oxidation reaction when you have 2 thiols that come together. And the oxidation we're talking about here is the loss of H2. Remember, that is one definition of oxidation. And in this case, the loss of H2 actually comes from a hydrogen from each of the thiols. So the hydrogen is attached to the sulfur on each of the thiols actually come off, and that gives us H2. And what you're left with is essentially what is left over. So basically, you're left with this guy and this guy. And basically you get rid of the H's and put both of these guys together. So again, as we talked about, kind of the easy thing to do is just copy what's there. In this case, we would end up with a CH3 and S connecting now to this S. So coming from this S to this S, and then CH2 and CH3. And this would be the product that would be formed here. This sort of connection here where we see two sulfurs together happens in amino acids that have sulfur, like cysteine, makes a special type of bond, which is referred to as a disulfide bond. So this kind of sulfur to sulfur connection there is a disulfide bond, or sometimes people call it a disulfide bridge. And like I said, it actually occurs in some amino acids, especially cysteine, which again does have sulfur in it. It makes this kind of important little bond. If we wanted to get rid of it, we can basically do the opposite of it. So we could do the reduction reaction. So let's just say we started with that guy. It was something like this. Oops, not plus yet. There we go. So let's say we started with this guy that has the disulfide bond. If we wanted to break it apart, we would actually just put the hydrogen back in. This would be a reduction reaction. And basically hydrogen, basically one would go here and one would go here. And basically we would break the bond right there. So we would break that bond and we would end up with two thiols. Again, putting the hydrogen on one and then putting the hydrogen on the other. So putting it together to make the disulfide bond is taking hydrogen out and pushing both sides together, breaking it back apart. If you're starting with a disulfide bond bridge, you basically add hydrogen, which is again a reduction reaction, basically the opposite of this reaction here that we just looked at, and you can break it back apart into the individual thiols. So in terms of thiols, what you need to know is the functional group, which is SH. You do need to know these two reactions here, the oxidation reaction where we take out hydrogen, squish everybody together, make the disulfide bond. And you need to know the reduction reaction where we have a disulfide bond and we want to break it. So we put hydrogen in and break it apart. Any questions on thiols? We will save no naming on thiols here. Any questions? The next sort of organic group we're going to talk about is ethers. And ethers are another organic group which basically has a functional group of basically a carbon, oxygen, carbon run. So that is the functional group. We have our oxygen stuck there in the middle of two carbons, and that is how we go about naming ethers. Has a bent structure like water, and that's because in the middle, this is what we got going for, electron pairs and two bonds. So that gives us a bent geometry, just like what we see in water. That also has 4 electron pairs and 2 bonds. Has a common name that gives the alkyl names and the attached group, and basically just put ether at the end. So common name, for example, here, very simple to do the common name is basically you find your oxygen that is between the 2 carbons, and you look to the left and you find what group you got there, and that obviously is a methyl group. We look to the right and we see a methyl group. That is 2 methyl groups within the same compound. So that is where the name comes from, dimethyl. And then we simply add ether to the end of it. And that's the way that we go about sort of naming these ethers, sort of the common name of these guys. So why don't you try one here? Let's say we had Obviously, you would put the groups in alphabetical order, would be the way to do it. Let's do this. All right, so why don't you take a second here and come up with the common name, find the groups, and put them in alphabetical order, and then just put ether at the end of it. Have carbon, oxygen, carbon. So that is our functional group. And basically, we want to just kind of focus in on the oxygen, and we just want to look to the left, basically, and to the right of it and see what we got going on there. So on this side here, we have a 5 carbon group on the left. So 5 carbon would be a pentyl group. Over here, we have a 2 carbon group, which would be a ethyl group. Again, put in them in alphabetical order, ethyl first, followed by pentyl, and followed by ether. So ethyl, pentyl, ether. Again, go to the oxygen as sort of your centerpiece, if you will, left and right, find the groups. Question on that. So I think for us, we would go with the common names here for our ethers. The more IUPAC way of naming is a little bit different. In the IUPAC way of naming, we would go with our longest carbon group, which in this case would be pentane, and that would be the base of the name. This guy would get oxy at the end of it. So instead of ethane, it would be ethoxy pentane would be the name. Ethoxy for the smaller group, pentane for the larger group, and that's the more IUPAC way of naming this. But we'll stick with for ethers common name as the way that we go about naming it. Just like down here, this guy here would be something like methoxy, because methane is the smallest group and also the largest group here. Methoxymethane would be more of the IUPAC way of naming this guy. Any questions on that there? But for us, common name should be sufficient. Here again, we see if we go to basically the right and left there of our oxygen, 3-member group, which is a propyl group, 1 carbon group, which is a methyl group, alphabetical methyl propyl ether. Again, here the longer group is propane. And if we went the IUPAC way of naming, it would be propane at the end. This would be methoxy. It'd be something like methoxypropane and IUPAC way of naming. But again, we'll stick with more of the common name. Any questions on that there? Okay, so in terms of ethers, obviously they're used as as anesthetics, as kind of puts you to sleep, obviously, which is really good, obviously, when you're taking surgery or maybe having surgery or something like that. Ethers were used for this purpose for a lot of years. Over the years, they've sort of changed out some of the hydrogens on ethers with fluorines, and they just found it a little bit easier to work with, not as flammable, which is good, and a little bit less of side effects. So nowadays, there's a lot of fluorines that are sort of substituted out for those hydrogens. And again, it just gives ethers a little bit better of some properties. Now, in terms of ethers, what you need to know is, again, functional group, what it is. You need to be able to name ethers using the common name. Any questions on that there? So why don't we take a second here and just review some of the stuff we've been talking about. Let's draw the structures for 3-pentanol, ethanol, and diethyl ether. So take a couple minutes, see what you come up with. Look, and obviously when we're drawing all these, as we've talked about, really want to proceed in this direction. So really the first thing we see here is OL, which tells us it's an alcohol. We see basically pentane, which tells us it is 5 carbons. So again, that is where you want to start with. OL alcohol on carbon number 3. So for me, I'm just going to go left to right, and that would be carbon number 3. In this case, you go either way, it gets you there. Just like everything else we've done, everybody else is going to be hydrogens to get carbon to 4. So he needs 3, needs 2, just needs 1 hydrogen, needs a couple, and needs 3 in this case. So that would be our 3-pentanol. Any questions on that one there? Rolling this way, again, we see OL, which tells us it's an alcohol. We see ethane, which tells us it really is just 2 carbons. And because it's ethane and there's only 2 carbons, you really could put the OH on either side. I'll just put it over here on the right. That means that this guy needs a couple of hydrogens and this guy needs 3. So that would be our ethanol. Again, here we don't have a number for this because if it's over here, it's carbon 1. The other option would be over here, which means it was carbon 1 as well. Third one here is an ether. So we want to think about sort of the connectivity of an ether, which is this. And then diethyl means that on each side we have an ethyl group. Ethyl group would be a 2-carbon group on either side. And obviously filling in our hydrogens at this point gets us something that looks like this right here. Any questions on any of those there? So let's talk a little bit about some of these properties of alcohol, some of which we've talked about a little bit before. An alcohol containing hand sanitizers is typically about 60% by volume. Ethanol can be as high as 85. Alcohols are soluble in water. And again, alcohols are soluble in water because they contain the OH group. So alcohols here and water are good usually because they could basically do some hydrogen bonding between them, between the oxygen of one, hydrogen of the other can do these hydrogen bonding. Solubility of alcohols about 6 or less carbons are very soluble in water. You get above 6, then you really do start to see a decrease in the solubility. Again, because once you get a lot of carbons in a row, and maybe all you have is just this one little spot where the OH group is at, you have this really big non-polar spot that gets in the way, and it creates what is sometimes referred to as steric hindrance, which is a fancy way of saying there's just a lot of non-polar carbons and hydrogens in the way, and it doesn't allow water to effectively sort of interact as it would because it's got this big non-polar part kind of blocking the access to water. So alcohols are definitely very soluble in water because they can hydrogen bond. They also typically have very high boiling points because they can also hydrogen bond. So remember, hydrogen bonding is a very strong intermolecular force, which means because it's very so strong, we do see higher boiling points, for example, in things with water than you would in an alkane, which does not have the ability to do so. An alkane, for example, can only use dispersion forces, which are those really, really weak versions of those intermolecular forces. So the stronger the intermolecular force, the higher the melting point, the higher the freezing point, and the higher the boiling point we typically see. We talked about this in terms of classification. Again, looking at the carbon that has the OH group, 1 a carbon attached primary, carbon that has the OH group, 2 carbons attached secondary, carbon that has the OH group, 1, 2, 3 carbons attached. Again, here making a tertiary alcohol. So take a second here and let's go with the classification. So are these primary, secondary, or tertiary? Okay, so again, always the carbon that has that OH group attached is what we're looking at. So directly attached to this carbon again is one carbon, two carbons. So this would be a secondary. This is the carbon that has the OH group attached. Attached to it directly is just one carbon, which means this would be a primary. And lastly, this is our carbon that has the OH group attached to it. And directly attached to that is one carbon, two carbons, and three carbons. And that would be a tertiary alcohol. Any questions on that? There. Okay. Alcohols, as I mentioned, has the ability definitely to hydrogen bond. So remember, again, for something to have the ability to hydrogen bond, it doesn't need to be a hydrogen attached to a nitrogen, oxygen, or fluorine. And that's a really strong sort of intermolecular force to have the ability to hydrogen bond. And again, that usually translates to very high boiling points and melting points. And because of that, it works really well with water, as I mentioned earlier. But if we do get really, really big, as I mentioned there in the last slide, again, this kind of non-polar part, even though it's got this small little part here that can interact with water, because this part is so big that's non-polar, it sort of blocks the ability of water to interact well with the alcohol. We really don't see that too much with smaller alcohols. Again, less than 6 carbons is kind of the key there. Remember that when we talk about solubility, it's like dissolves like, which means again, polar and polar things are really good together. Non-polar and non-polar things are also very good together. But when you cross over to that polar, non-polar situation, those guys are definitely not so good together. So here's a chart of some alcohols, number of carbons, and again, you can see sixes, in this case, five, in this case, 5 or 6 carbons, solubility really starts to decrease. So as we start increasing the number of carbons, the solubility really decreases a lot. And again, here, there's just one carbon there, or 2 carbons, sort of 3 carbons, 4 carbons. But again, we're now starting to build out a very big molecule that has this non-polar part, which makes it really difficult to sort of interact with water. Remember, in order for something to sort of interact well with water, you basically have to break apart water and water interactions and replace them with something that's similar. So water is a relatively small molecule, so it starts to have a little bit of a situation when you try to sort of put in there something that's really, really kind of big. Again, maybe I've used this example before. If you park a car in a garage, it fits pretty well. If you try to park like a semi truck in a normal garage, yeah, maybe you get part of it in, but the rest kind of hangs out. It doesn't really fit really well. And it's sort of the same idea when we try to get things to dissolve in water, sort of mix with water, is we really need to replace these sort of interactions that we see when water sort of behaves with water with very similar ones. And it really is unable to do so when we start to get really larger molecules. Any questions on that there? And obviously, hand sanitizer, again, containing ethanol or propanol as their active ingredient. Pretty relevant out of these days and age. There's hand sanitizer everywhere. But you do want to make sure, again, obviously, it's appropriate sort of percentage by volume there to sort of be effective. So minimum is usually 60, can be very high in some cases in terms of those contents. Now, we also talked about phenols the other day as well. Phenols are basically benzene rings that have an OH group on it, sort of a special class, if you will. They are slightly soluble in water because they do have the OH group. They can react with water to form a phenoxide ion. And basically what's going to happen is sort of an acid-base reaction. So our phenol here will basically donate its H plus over. And again, that is sort of its like conjugate base, if you will. And obviously when the water accepts the H plus, it's acting as a base. And this would be sort of its conjugate acid. So kind of like our Bronsted-Lowry stuff that we were talking about when we talked about acids and bases, is sort of the reaction that we see with a phenol and water, which makes it relatively soluble. Let's talk about a little bit about solubility here. Let's take a look at both of these here and determine which of these would we expect to be soluble in water and explain why. The first one, if we look at, they both have alcohols. They both have the alcohol functional group, I guess is the way of saying that. They both would technically have the ability to hydrogen bond with water. Again, here, water being more negative on the oxygen, more positive on the hydrogens. And again, that alcohol that has the exact same group, basically, able to do the hydrogen bonding between the hydrogen of one and the oxygen of the other. This guy here, though, 1, 2, 3, 4, 5, 6 carbons. This part of the molecule is really non-polar. This part is polar, but because this part here is relatively big, it's going to be big and non-polar and probably would make this thing insoluble in water. Because of that, again, just not going to allow water to effectively interact well with this molecule because of its size. Opposite is true here. We got a relatively smaller molecule, also has a non-polar part, also has a polar part here. And again, because this guy is not very large, maybe a little bit larger than the water, but still on the relatively small size, it's going to be able to interact well with water and also be able to hydrogen bond with water, and thus be soluble in water as well. Any question on any of those two there? Are alcohols sort of in general? Okay, then we're going to continue on in our journey here of organic molecules, and we're off to our next two sort of major groups. And our two major groups are aldehydes and ketones next. So let me see if I get this going here. There we go. So aldehydes and ketones are two carbon containing groups that are organic molecules, and they obviously have oxygen involved. They contain basically a carbon oxygen double bond as the main part of their functional group. So this group right here, which is the carbon oxygen double bond, which is sometimes referred to as a carbonyl group or a carbonyl carbon. It's a fancy word for a carbon oxygen double bond. It's actually a polar group. The oxygen is more negative here. The carbon is more positive in this group. And aldehydes have a functional group of carbon oxygen double bond with a hydrogen. So that is the functional group of an aldehyde. Ketones, on the other hand, we'll go this way. Ketones have a functional group of 3 carbons in a row, where the center carbon basically has that carbon oxygen double bond. So this is the functional group. Functional group of a ketone. So they both share the same kind of carbon oxygen double bond, but there is definitely a difference in their locations of where these functional groups are in the molecule, as we will talk about, and some of the properties as well. The simplest ketone is acetone, or propanone, which is sometimes referred to as dimethyl ketone. It is a colorless liquid, obviously used to remove paint and nail polish and stuff like that. The simplest ketone you could have is propanone, which is based off of 3 carbons, because you need 3 carbons to make a ketone. That is pretty much the simplest guy that you could actually make that would be a ketone. On the other hand, the simplest sort of aldehyde you could have is basically a 1 carbon guy, because you have that guy there at the end. So let's take a look at these guys. Aldehydes and ketones, again, as I mentioned, have that carbonyl group. It is polar. It cannot hydrogen bond because it does not have a hydrogen, obviously, here attached. But it is polar, which means it can hydrogen bond with somebody else. And what I mean by that is, if this is our carbon oxygen, this is again more negative, this is more positive. If it comes across somebody like water, for example, where we have negative and positive, it can hydrogen bond with something like water, but it cannot hydrogen bond with itself because it's missing, obviously, a hydrogen to do so. It's a very electronegative arrangement. If you look at the periodic table, carbon, nitrogen, oxygen, fluorine, remember, electronegativity increases this way. So we're talking about a bond between these 2 guys. So it is definitely a polar bond, and we do get those separation of charge. The aldehyde is attached to a carbon atom and at least 1 hydrogen atom. Ketone, again, always has that sort of 3 carbon run. Because of the aldehyde group and it having basically the hydrogen as part of its functional group, the aldehyde group, which is this guy, must always be at the end of a molecule. So this guy always has to be at the end, because it goes back to the basics that we talked about with bonding. Hydrogen can only have 1 bond, right? Or 2 electrons. So you can never have this group in the middle of the molecule. Otherwise, hydrogen will end up with too many bonds. So you'll always find the aldehyde group either like on one end or the other, but it will never, ever be in the middle. Different than that is the ketone group will always like be in the middle. Basically, that carbon oxygen part will pretty much always be sort of in the middle of the molecule, because you cannot have the carbon oxygen bond there at the end, because it needs that 3 carbon run, which means you'll never find this guy sitting at the middle, I'm sorry, sitting at the end of a molecule, because it needs those 3 carbons to have a ketone. At least 3 carbons, can be more, but minimum 3. So you'll never ever find that carbon oxygen at the end of the molecule. As you see here, in this case, is in the middle. This guy is basically at the end of the molecule because of that. Any questions on that there? Now, sometimes in sort of condensed formula, you'll see these things written like this, CHO, and that again is our aldehyde group. That basically is a carbon oxygen double bond and a hydrogen. And sometimes you'll just see sort of CO written as the carbonyl group, which is our guy right here. And here's our way of, sometimes it can be writing. This is obviously drawn out. This is sort of more of a condensed formula. And this is what it looks like in line structure. Again, when we look at something like this, guy at the end is actually a hydrogen because we wrote hydrogen. Again, that is our carbon there. And that is our carbon oxygen double bond and our hydrogen. And for our ketone, again, looking like this for condensed, are looking like this for line. And again, this is a carbon, carbon, carbon. So there's our 3 carbon run that's necessary with the double bond in the middle there for our ketone. Any questions on that there? So let us talk about how we go about naming aldehydes. Aldehydes, not too bad. We basically put Al at the end of it. So longest carbon chain, we basically go Al at the end of it. And if there's any other groups attached, the carbon oxygen guy, this guy right here, that carbon gets the priority in numbering. So this guy is always carbon 1. And then if there happens to be other groups attached, it would be named similar. So if we had basically the simplest one you can have here, which would look like this. This is an aldehyde, has 1 carbon. 1 carbon is based off of methane. We drop the E and we put methanol, Al. And that would be the name of it. By the way, one with 1 carbon has a common name known as formaldehyde. So formaldehyde and methanol are both the same thing. You should be familiar with that. People use formaldehyde a lot. Again, so methanol and formaldehyde, basically the same thing. If we had 2 carbons, this would be 2 carbons based off of ethane. E gets dropped and becomes ethanol, Al. There is absolutely no need to give the location of where the carbon-oxygen double bond is located because it always has to be at the end, which means it always has to be carbon number 1, no matter what the case is. So there is no need to give a number like we do with, say, alcohols or things of that nature, or double bonds. So why don't you try one here? Let's just say we had, let's go with this. Let's go with, oops, let's go with that. Let's do that. All right, so why don't you take a second and see what you come up with in terms of the name of this guy here. Okay, so let's take a look here. So really, we want to kind of follow the same stuff that we've been doing before. We're looking for the longest carbon chain. Clearly, in this case, this is the functional group. So that's got to be part of it. And that looks like 1, 2, 3, 4 carbons. And then we also have a group that's attached over here. So 4 carbons is based off of butane. Whoops, butane. This is obviously our aldehyde group, which then becomes butanol, Al. This has to be carbon 1 because that's the priority, which means this has to be carbon 2. That has to be carbon 3, and that obviously has to be carbon 4. That means that my chlorine group there is on carbon number 3. So this would be 3-chlorobutanol. So because we don't actually give the number of that carbon oxygen double bond, it is carbon 1. So if there happens to be other groups attached, they are numbered accordingly. Any questions on that one there? Okay. So here's a few: propanol, butanol, ethanol, and methanol again, and what they look like in line structure here. Basically 1, 2, 3, 4 carbons, butanol, 1, 2, 3 carbons, propanol based off of propane, and so forth. So why don't you give the name for this guy? And let me maybe, let's see here, give a couple other ones maybe for you to give a go at. Why don't we try why don't you name that one as well? And then why don't we go with let's do 4 chloral 5-methyl octanol. All right, first two proper names. The last guy, draw it. See what you come up with. Okay, let's take a look. We'll start the guy over here on the right. Still want to do our longest carbon chain, and in this case, it looks like it is straight across. So that is 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons. Really, your only other option would have been to go this way and then down, which obviously only gives you 3, which is definitely not enough. And you may be asking, could you have gone, kind of from the left here and then down? The answer would be no, because you would be excluding the aldehyde group. So it would not be okay to go this way and then down, because that leaves out the aldehyde group that's over here. So remember that your longest carbon chain should contain the actual functional group as part of it. So we got 5, it looks like, straight across. So 5 with the functional group that's an aldehyde becomes pentanol as the base of our name. We don't need to give the location of this because that's always going to be carbon number 1, which means that carbon number 2, that is where we see our group. And that will then wrap it as 2-methyl pentanol. Any questions on that name there? Same idea on the next one. Here we're going to go 1, 2, 3, 4, 5. We could have also went 1, 2, 3, 4, 5, and they're both the same. So as we've talked about previously, if you have that option, why not just go with the straight one straight across? We again see our aldehyde group right there. And that was 5 again, actually. So again, the base of our name here going to be pentanol. This has to be carbon 1, which means this is carbon 2. That's carbon 3, where we have a bromol group. And that would be carbon 4, where we have a methyl group. And put in alphabetical order, we'll go with bromol before methyl. And that would be 3 bromol, 4 methyl pentanol, Al at the end of that. Any questions on that name there? All right, so lastly here we have a name, so we want to work ourselves backwards here. Octanol, Al tells us it's an aldehyde, which tells us we do have this group at either end. Since you're drawing, you can put it at either end. I'll just put it there. Octanol means octane, which is 8 carbons. So I'm just going to add in my other 7 carbons here. So that's 1, 2, 3, 4, 5, 6, 7, and 8. That takes care of that. Remembering that because I put my group right here, that has to be carbon 1, which means that's carbon 2, carbon 3, carbon 4, carbon 5. I have a methyl group. Takes care of that. Carbon 4, I have a chloral group. Takes care of that. Everything else here going to be our hydrogens. Just like we've done previously, we want to make sure we end up with 4 bonds to carbon. So looking at this guy here, he needs 2. This guy also needs 2. This guy just needs 1. Guy next to it also just needs 1. This guy needs 2. This guy needs 2. And the guy at the end there needs 3. Any questions on that structure? Naming aldehydes or drawing aldehydes? Any questions on them? Then let us talk about then the way we go about naming ketones. So maybe not surprisingly enough, ketones ends in O-N-E, and that is pretty much kind of how we end the name of ketones. You could drop the E and put O-N-E. at the end of the alkane name. So the simplest ketone you could have, because it needs 3 carbons, would be this guy, 3 carbons based off of propane. Drop the E, and this is propanone, O-N-E. Over here is butanone, which is 1, 2, 3, 4 carbons, butane. Here is the ketone part of it right there, and that would be known as butanone. Now, when we get to 5 carbons, though, this is 1, 2, 3, 4, 5, based off of pentane. Drop the E, it becomes pentanone. We do need to give the location of where that carbon-oxygen double bond is located. In this case, no matter which way you go, it is located at carbon number 3. So that is why it's called 3-pentanone. The 3 is the location of the carbon-oxygen double bond. So as you can see here, once you get about 5 or more carbons in a ketone, you do have to give the location of that carbon-oxygen double bond, and you would do whichever way gives the carbon-oxygen double bond the smaller number. So we do want to give that guy the smaller number, and everybody else that would be attached would be named accordingly. In this particular case, we do see sort of a ring structure here at the end. This thing right here is our ketone, carbon, carbon, carbon. So that is a 3-carbon run with a double bond attached to a cyclohexane ring. Drop that, that becomes cyclohexanone. Do not need to give the location of this guy because it will always be carbon number 1 in here, but that means that carbon 2 and carbon 3 is where we have a methyl group, and that would give us 3-methyl cyclohexanone. Again, smallest number in doing so. Any questions on that one there? Okay, why don't you try one here, see what you come up with. Maybe, there you go. Take a second here and see what you come up with in terms of the name of this ketone group right there. So looking for our longest continuous carbon chain, 1, 2, 3, 4, 5 straight across. 1, 2, 3, 4, and then down gives us 5 as well. So you get 5 no matter which way you go. So might as well go with the straight. So 5 carbons in a row is pentane. We see our ketone group as we talked about. So this becomes pentanone, O-N-E, is 5 or more carbons, which means we do need to give the location of this carbon-oxygen double bond, and we want to give it so it is the smallest number, and that would be doing right to left numbering. Going right to left, we see that the carbon-oxygen bond is at carbon number 2. Obviously, if we went right to left, we would put that bond at carbon number 4, which would be too big. So we don't want to go that way. So that means that carbon number 2, we have the carbon-oxygen double bond. So that is 2-pentanone. Because we have now locked our numbering into place going in this direction, we can clearly see at carbon number 4, we got our good friend methyl hanging out there. And this would then be 4-methyl 2-pentanone. Any questions on that one there? Let's try a couple here. Let's go with, why don't you draw 4-chloral 2-hexanone. Hexanone. There we go. Why don't you also do 3-bromol 5-methyl 2-heptanone. And why don't you give this guy a name here? Let's do all right. Oops, maybe. There you go. Let's fix that there. Okay, so draw the top two and give a name here to our bottom guy. See what you come up with. If I finish it here, there you go. All right, so take a moment or two to see what you come up with. Okay, so again, we're going to work our way backwards here. So ONE tells us it's a ketone, and hexane tells us really there's 6 carbons involved. Might as well start with that. So just lay up your 6 carbons. That's 6, I think. There we go. And again, because you are drawing, you really can go left to right or right to left. I personally am going to go left to right, which means when I see 2-hexanone, I know at carbon number 2, that is where really my carbonyl group is. And now I have my ketone right here, basically carbon 1, carbon 2, carbon 3. That is my 3 carbon run with the double bond. Because I chose this as my carbon number 1, when I now get to 4-chloral, that means I have to put my chlorine over here, as that would be really carbon number 4 going down the road. At this point, we're out of stuff. So that means we fill in hydrogens. So a couple there, 1 there, a couple there, actually none here, and 3 here. So there we go. Any questions on that one there? Working the next one here, heptanone. Again, ONE tells us it is a ketone. Heptane tells us in this case we're working with 7 carbons. That's 7, 3, 4, 5, 6, 7. I am again going to go left to right. So for me, that would be carbon number 2 right there. And that's where I'll put my ketone group. Again, 1, 2, 3 carbon run with the double bond in the middle is our ketone. Because I call this carbon number 1, at carbon number 5, which would be right here, there is a methyl group. And at carbon number 3, which would be right here, there is a bromine. And I believe that's all she wrote on that. So we will add our hydrogens in, 3 at the end, 2 there, just 1 there, 2 there, just 1 there, none here where the ketone group is, or the carbonyl group, and 3 there. Any questions on that particular one there? All right, looking at the last one here, this hopefully you saw is not a ketone. It's actually an aldehyde group. So we're looking for the longest continuous carbon chain that contains that group. And hopefully you saw this one, 1, 2, 3, and then you went down 4 and 5. So that right there is actually the longest continuous chain. Obviously, if you went straight across, you would end up with only 4 carbons, which is obviously less than 5. 5 carbons with the aldehyde group at the end is going to be our pentanal, Al at the end. This has to be carbon 1 because that's where the carbon oxygen double bond is located. That means that's carbon 2. We have a bromol group. Carbon 3, we have a methyl group. And again, here alphabetical, we're going with B before M. That gives us 2 bromol, 3 methyl, no need for the dash really, 3 methyl pentanal, Al at the end of it there. Any questions on any of those there? How to name, draw ketones or aldehydes? Okay, then let's talk about some properties of aldehydes and ketones in water. As I mentioned earlier, even though they cannot hydrogen bond with themselves, they can hydrogen bond with water. So they can hydrogen bond with water, which makes them soluble in water when they have, there is a limit, about 4 or less carbons. So once you start adding more carbons, much like anything else, it does sort of decrease the solubility. A reminder that the hydrogen bonding here is actually in the aldehyde happening at the carbonyl group, and again with water, the oxygen and the hydrogen water able to interact in a small aldehyde. Same thing happening here with our ketone group, the exact same interaction. Again, with our ketone group, the oxygen and the hydrogen there in water are going to be able to interact. 4 or less carbons, we start to definitely see a decrease in the solubility once we go above that. Again, not able to hydrogen bond with itself, but able to participate with hydrogen bond because the other compound, water, has the ability to hydrogen bond here. As you can see here, 1 through like 4 carbons, really soluble. These are both aldehydes and ketones. And again, slightly soluble as we get to 5. And when you kind of hit 6 or more, not really soluble at all. So slightly soluble is almost leaning towards being insoluble, but a little bit will be able to dissolve. But pretty much hitting that 6 on an aldehyde or a ketone, pretty much your solubility pretty much drops right out because, again, it just gets too big for water to be able to get in there and really interact well with the aldehyde or ketone. Any questions on that there? Now, in terms of, for example, boiling points and things of that nature, obviously alcohols, which has the ability to hydrogen bond, is the highest. Aldehydes and ketones would kind of fall below alcohols in terms of boiling point, and obviously alkanes would be at the lowest end of it. So they kind of fall in the middle of those two. Again, alcohol's the highest boiling point because of its ability to hydrogen bond. Here's some important aldehydes and ketones. I'm not sure where that guy went on the left there, but it should be this guy, CH3C double bond. Oh, CH3. Propanone, as we talked about before, also known, by the way, like we do with ethers, that is a methyl group. That's a methyl group. So common name, dimethyl ketone is a common name. And that's just like what we do with ethers, groups on each side of the carbon-oxygen bond. And we can kind of use a common name there. You should use the IUPAC way of naming, but again, you'll sometimes see that common name used. This is methanol, which is also known as formaldehyde. So you should know both of these names are the same thing. And obviously it's used to preserve biological specimens. So if you ever taken biology, you probably have seen it. Some other important aldehydes and ketones, benzaldehyde, kind of what we see in almonds. Vanilla here is our aldehyde here. There's the aldehyde group. And over here, this is basically cinnamon, and that is our ketone group right about there. And obviously, benzaldehyde is a benzene ring. And that's where sort of the benzyl part of comes from. And then the aldehyde is just the aldehyde part of it. All right, so let's classify each of these as either a ketone or a aldehyde. So let's take a look at this first one here. Hopefully you can see that this is a ketone, and that is 3 carbons in a row with the double bonded there on the 3rd carbon. So that part right there is our ketone part. This part right here is our carbon hydrogen carbon oxygen double bond and hydrogen. That is an aldehyde. Over here again, this is our aldehyde. And lastly here, carbon, carbon, carbon. That is a 3-carbon run with a double bond in the middle. So this part of this molecule here is our ketone. Any questions on that there? Okay, so let me see here. We'll skip this one for just now. I think we talked about these guys earlier here. So we'll skip this for just now here. We did this earlier on. Did that one there. I just want to talk about aldehydes and ketones and some of the processes that occur with these aldehydes and ketones, and really 2 important tests that you could run to determine whether or not you sort of started with an aldehyde or you started with a ketone perhaps. And one is the tolerance test, the other one's the Benedict's test. Remember that we do create an aldehyde from a secondary alcohol, right? So, I'm sorry, an aldehyde from a primary alcohol, my mistake. Primary alcohol would be a better way of saying that, the correct way. And so if we had our primary alcohol here, right, and this is ethanol, when we go through the oxidation process like we talked about, we will take out a hydrogen here, take out a hydrogen here, and make that into a double bond. And we would get what we now know is ethanol. And if you remember, we talked that we could actually take this guy through one more oxidation. And in this case, we're actually going to add oxygen in right to the hydrogen at the end. And we get what is known as ethanoic acid. This is a primary alcohol, gets oxidized to an aldehyde. And if you continue to oxidize it, it gets all the way to a carboxylic acid is what this is. Carboxylic acid functional group is this group right here, carbon oxygen double bond and the OH. Now, if you take a secondary alcohol, like this guy, and you oxidize it, H and H come off, and we end up with what we talked about earlier. This is a secondary alcohol that ends up as a ketone. This right here is 2-propanol, which is a secondary alcohol, ends up in what we now know as 1,2,3-propanone, O-N-E. When you oxidize this one more time, nothing happens because there's no hydrogen here, so no reaction occurs. So we can use a test known as the tolerance test, which uses silver. Silver is going from +1 here to 0. It is going from +1 to 0, which means the silver is being reduced. The aldehyde here is being oxidized in this case. And when this process occurs, we oxidize our aldehyde to a carboxylic acid, as we see here. And the result of that is the silver, which starts out as an ion floating around in the solution, becomes out of solution and becomes solid silver, which is why this is sometimes referred to as the mirror test. You see this really silver, obviously, color that occurs, and that is a positive test for the presence of a carboxylic acid. And that means that we did start in this case with an aldehyde. Now, if we ran the same test on a ketone, nothing would happen. So it wouldn't go through oxidation. So if you ran this test, it would stay sort of the solution color. You wouldn't get this solid silver color, and that would be a negative test for the presence of carboxylic acid, which means you could probably maybe assume that you started with a ketone rather than an aldehyde. Another test that I think you do in lab there is the Benedict's test. And the Benedict's test is also a test you could use to go determine if you started with an aldehyde, say, versus a ketone. Same thing here, the copper gets reduced. It goes from copper with a +2 charge to copper with a +1 charge. It oxidizes our aldehyde, and we get this ketone color, or we get this carboxylic acid that occurs. And the process of this is copper 2 that we start with is a blue color, ends with kind of like a orangey color, yucky orange brown type color, reddish color, which indicates the copper 1 ion has been formed. And if you do get this sort of orangey color occur in the test tube, that is positive that you started with an aldehyde. And if you don't, and it stays blue, it is, I don't know if I have a picture of that. I guess I don't. I thought maybe I did. I do here. There we go. So this is what it looks like if it was negative. It's kind of orangey yellow type, really more orangey red type color is positive. And again, you would see this as a positive for an aldehyde. If a ketone was there, because it will not make a carboxylic acid, it will stay basically blue. So Benedict's test and the tolerance test are two tests that you could use to identify the presence of a carboxylic acid, which means in both cases, you started with an aldehyde was present to begin with that took you to a carboxylic acid. So in the case of the tolerance test, it would become silver in color. In the case of the Benedict's test, it would become, again, that kind of orange red color would signal a positive one, means your aldehyde went to a carboxylic acid. If you had a ketone, it would not go to a carboxylic acid. And obviously the tolerance test would not turn that mirror color. And the Benedict's test would stay probably more this kind of bluish color. And you would not see that, and that would be negative for that. So those are two very common tests for an aldehyde or a ketone. Any questions on that there? All right, we will lay it up there. We're pretty much done with this chapter.